Hi everyone, welcome to another one of these ZX seminars. Today we have Joe George, who will be talking to us about his master thesis research, um, which is a bridge between the ZX calculus and percolation theory.
hmm
So Joe, if you want to get started.
Yeah, well, thank you so much for having me. It's great to kind of go back and dive into this stuff again. Um, I've moved to the University of Cambridge now, so I'm kind of working on different stuff at the moment, but this will be a nice reminder of what I did for my master's thesis. And so here we're going to be revisiting um, this paper that came out in 2008, so quite a long time ago. And we're going to try and work through some of the ideas from there again from the perspective of ZX calculus, and then look at the tools of percolation theory, which are discussed in there, and hopefully see if kind of using both of these tools together can help us build insights for maybe developing on the methodology that originally occurred here. So the first thing I'd like to make clear, which I'm sure we're all comfortable with, is that computation is fundamentally a physical process. And because of that, we have to account for the fact that the real world is erroneous. It is not perfect. And so what we're going to look at here is the paradigm of measurement-based quantum computing. And in particular, we're going to be looking at errors from the perspective of how we build cluster states, so the resources that we're going to use for measurement-based quantum computing. And we're going to try and study if by quantifying the amount of error that occurs on these cluster states, whether we can get insights into whether they're even useful for performing computation. So this was the original paper, and it was published in 2008 by Dan Brown and a few others. And they basically derived an algorithm to explore, it's like a pre-processing algorithm to explore a faulty cluster state and try and identify a universal substructure beneath it. And we're going to kind of re-implement this, a slightly different twist on the algorithm to try and make some other arguments, but we're going to kind of look through how they did this and then see how we might extend on their work. So just as a quick reminder, we're going to talk about the quantum circuit model to bring it into perspective with measurement-based quantum computing. So I'm sure lots of us are familiar with just the standard paradigm of quantum computing, which is where we initialize a quantum state and then we subject to it to a circuit, which will consist of unitary operations, and that will modify the quantum state to a desired outcome. And then we use our own measurements to try and interpret that outcome. And hopefully this is the sense of computation. So the computation is really kind of, this is more reflective of sort of the classical idea of computing, where you just kind of push bits through a system and, you know, modify them into a state we want to use. So instead, what if we considered something that we call a graph state? So I've written this in the ZX notation. This is just a little chunk of a graph state. And we start with this quantum resource. And then what we're going to do on this quantum resource is make measurements, which is great. That lends itself to the name measurement-based quantum computing. And measurements here, measurements are interesting because they are non-deterministic, but they are one way. Once you've done them, you can't go back. So, which is why, you know, in 2008, they were calling this the one-way model for quantum computation. But here we'll just call it measurement-based quantum computing. And so essentially, if you make measurements, careful measurements on the cluster state, you can end up manipulating, with the ZX that makes it clear, you can manipulate what you end up with to a desired quantum state. And in fact, this outcome here is just a Bell state, except we don't know which type it is yet because we haven't actually accounted for the undeterministic measurement. So K1 and K2 here will just be integers between 0 and 1. And then depending on what the outcome is, we can adapt future measurements to try and correct these. And so that's what I'm going to quickly mention here, which is the process of feed forwarding. So that's just the idea that you can account for the uncertainty in the measurement in future measurements you make on the system to try and cancel out those phases that occur. So I've just done like a little, this is based off, a lot of the stuff I'm going to talk about at the beginning here is based off the Quantum Processes book. And so we're just making measurements here and we kind of pass forward the errors so that we, in future measurements, can account for them, to negate them. So the point being is measurement-based quantum computing starts with a resource. You make measurements to essentially carve out the equivalent of the quantum circuit model. And then if our cluster state can be correctly time ordered, which is that we can make these feed-forwarding corrections, then we can make this outcome deterministic. And we're going to assume from here that the clusters that I'll be introducing can be correctly time ordered. And so we won't have to worry about that. But one thing I do want to cover again quickly is this notion of universality. So this is just the ability to implement any desired unitary operation on the gate so that we can essentially perform any computation we desire in quantum computing. And so what we need to do that is we need to implement any single qubit unitary, which I've written in the Euler decomposition below there, and just the ability to implement a CNOT gate. So again, to give a quick example of what this might look like, we're going to consider the brickwork lattice. And if we look at a single brick here, which is just kind of a collection of 5 nodes, these kind of bricks, I wish I could put a mouse on here, but I can't. But if we consider a little brick here, we're going to look now at how we might create the desired universal single qubit gates in the CNOT gate to show that it is it is a universal structure. So ignoring kind of corrections that we would make with feed forwarding and stuff, we can essentially show the unitary gates being created here. And then for the CNOT gate outcome, we have the same thing over here. Right, so essentially we are interested in the notion of universal structures because those allow us to do any desired computation. And the ones we have that we've explored here is the brickwork, but in general, it can extend to other geometries. So the regular triangular lattice, the square lattice, and the hexagonal lattice are also universal and can be correctly time ordered. Okay, so this is great. So we have we know that these cluster states that we're going to use, the resources for measurement-based quantum computing, if they are of interest to us, they must be universal. Here's the thing, is when you're constructing these states, it's not absolutely perfect. The actual physical process of building these is not necessarily perfect. And so we're going to consider two kind of paradigms, we could say, of creating these cluster states in the physical sense. So we'll call the first one the static approach, which is just kind of where you would lay out, your qubits would kind of be laid out physically, and you hope for some kind of interaction. You can also actively perform these interactions between them, but you'd essentially, like if you had you could lay out a bunch of atoms in optical lattices, and you hope that they have an Ising type interaction, which would manifest the equivalent of the CZ gate between the qubits. And this would construct like a gridded lattice, so it would build a graph state. Now, the problem with this approach is that although you can have CZ gate failure, so kind of the interaction doesn't manifest, you can correct it using a thing called lattice surgery. So you kind of like carve around that atom and try and reinitialize the interaction. But in the case of a failed qubit, so you can deal with atomic loss in this setting, where essentially you're just left with a deprived region without a qubit. And so it's a lot harder to account for these errors because you kind of have to reinitialize the entire process. And then for the dynamic case, we would be dealing sort of with, this is like the photonic model or like linear optical quantum computing, where we basically initialize photons, again in the plus state, and we try and actively entangle them. And in this case, they're kind of like, we would literally be firing our photons through some system, and then we would actively entangle them to try and build a graph state. But again, these can be subject to photonic loss, and the actual implementation of CZ gates to build these graph states is non-deterministic for the photonic case. But we'll see here, like in a second, we'll kind of explore exactly what we mean by this. But essentially what happens is that our cluster states that we're building, they are subject to errors. And so if we have a failed CZ gate, in the terminology of percolation theory, this is known as bond percolation on the graph. And if we have a failed qubit, this is manifested as site percolation. So what we're dealing with here, because cluster states obey this kind of symmetry, this lattice-like shape, we're dealing with essentially a problem of percolation theory. So the question we ask is, at what point can a lattice be subject to errors and it still be useful? Because surely there's a point where you kind of run out of all the qubits and maybe that structure is no longer universal. And if it's not universal, well, we can't really use it for anything practical. But even if it is, we want to try and account for what we might adjust. How much must we scale then the lattice to return it to the original computational power that it should have had it not been faulty? So those are the two ideas we're going to explore. So these are some classical results of percolation theory, which basically tell you about spanning largest connected components on graphs that we're dealing with. So percolation theory is kind of like a branch of mathematics that deals with like the removal of edges and nodes on a graph and looking at how the structure of this graph changes as you remove them. But percolation theory is defined usually in like the thermodynamic limit. So we're imagining an infinitely large region to deal with. Now, this might seem silly because we're obviously not building infinitely large cluster states. But the results hold very closely once you've got finite n and it's large enough. So even with small values of n, the results start to approximate very well. So these critical value probabilities are actually very close in the finite case as well. And so we're dealing in percolation theory with three regimes of criticality. So if we define P to be the success rate of a node appearing. So here for my demonstration, we're dealing with slight percolation, which would be the equivalent of failed qubit on the right here. And essentially our probability is the probability of a qubit being there. So we're looking at kind of like the positive probability. So on the left, we'd be in the subcritical regime if only 50% of the qubits are present. And what this means is the largest connected component in the infinite scale case, in the infinite size lattice case, the largest connected component will always be finite. So it's going to be bounded to like a finite region. And the critical regime, it becomes like more ill-defined because this is the phase transition. It occurs at this value. But in the supercritical regime, we can guarantee that the largest connected component also infinitely spans the infinite lattice that it's in. So those are kind of like the three regimes. Basically, we're dividing them with two, and we have either a finite lattice spanning or an infinite lattice spanning. But we keep these ideas in mind that they also essentially hold for the finite scale. So in analogy to the original paper that Dan Brown discusses, we are going to quickly discuss what the shortest path algorithm does. And the shortest path algorithm explores the lattice, the faulty lattice, and tries to trace out an unfaulted universal structure within it. And we're going to use measurements to carve this structure out and see, first of all, we're going to see how this is possible, and then we're going to try and understand the computational power of the resource we're left with at the end. So as some tools to use that will help us essentially carve out this universal structure, we're going to pay attention to the effects of the Y measurement, which essentially manifests the local complementation on the graph about the vertex, about the qubit that you are measuring out. But we are interested, as we will be, mostly in the one-dimensional case at the bottom here. And essentially, the effects of the Y measurement is just removing this qubit in the middle and connecting the two neighbors together. So you're basically making it redundant. So this is a fun phenomenon. Y measurement has this trick in the setting of what it's doing on the ZX diagrams. The Z measurement does sort of the opposite thing, which is that it deletes the node that you were applying on. So again, in the one-dimensional case, when we're applying a Z measurement, we are just removing that qubit. So what might we do? So if we consider here again the slight percolation approach, and I believe we're dealing with a 20 by 20 lattice here, maybe it's 25 actually. I'm going to sort of make it to draw a parallel with the original paper. We're going to frame the qubits as a present qubit as a little blue square, and where the qubit's gone missing, this is just a white square. And we're dealing with slight percolation here to explain how the algorithm works. And so if you look at that little pink region, I've zoomed in and drawn on the right the equivalent in the ZX formulation. So this is what we're doing. And so what we're going to start by is we're going to go on the far left of the grid. Say we'll start at the bottom left qubit essentially, and then we're going to go all the way to the other side on the bottom right. And we're going to ask, is there a shortest path between these points? And the algorithm is going to find the shortest path, which is very easily implementable computationally. And just to be clear, a path is any walk on a graph that doesn't intersect itself via a node or via an edge. So you just want a path between these 2 points, between left and right. Under the condition that once we've drawn a path, if we move on, because we're going to climb up and draw more paths, that these paths can't intersect with one another. And this is important for, as we'll see, is for finding the universal substructure underneath. So this is the condition we're looking for. So we first of all, on the left-hand side here, we're doing left to right shortest paths, and we're working our way up. And then we'll do the same thing from top to bottom. So we're basically drawing a grid with a bunch of paths that have at least a space between them on this lattice. This is slightly different than the original algorithm, and it might actually be less efficient than the original algorithm. But as we'll show the results in a second, that first of all, they actually produce sort of the same predictions as the original algorithm. But we're using this more as a theoretical discussion, because using the shortest path perspective kind of helps us argue something that we'll get to in a second. And so from here, we just do some kind of nitty-gritty computation where we'll cut off little things called bridges, which I'm removing in C, to try and shape this into a hexagonal form. Oh, maybe I haven't actually mentioned, just to be clear here, the universal structure we're going to look for here is the hexagonal lattice. And the reason we're doing this is because a hexagonal lattice is, of the universal ones we looked at, is the one with actually the least mean degree. It's got a degree 3 between every vertex. So it'll probably be the easiest one to try and find, just to be clear. And then we do some further manipulations on this algorithm, which include kind of rewiring little, sometimes you get little clusters of paths and you want to kind of remove them and readjust them just to make sure that everything's put into the right shape. And eventually you end up with a path that's being traced here on the right that is identifying a hexagonal structure. Now, I want to make it clear that this is a pre-processing algorithm. We're not doing anything from the quantum computing perspective. This is just a classical algorithm that is analyzing the cluster state and trying to identify a structure. And then it's up to measurements now to perform on this grid based on the colorings we've put to actually retrieve this structure underneath. And the reason we've identified different colors here is because those will correspond to different measurements. And so essentially what we're doing is, if we look at anything that's left as a light blue qubit, we're just going to measure out, we're going to remove that. Everything that's a dark blue qubit, we're going to use the Y measurement because that sort of bridges them together, as we saw before. That's the effect of it. And then anything that's a junction, which we had been kind of, these were the intersections and we had readjusted them. Anything that's a junction, so the little black squares, those we leave unmeasured. And those will essentially become sort of the premise for the hexagonal cluster state. This is where the power comes in. And so we're left with this sort of cluster state. I've here put a little black dot for an input spider leg, but I'm just leaving it there to make it clear without having too many legs interfering on the graph. And ZX diagrams are topologically invariant, so this is just identically equivalent to a hexagonal structure. So essentially, we've used this algorithm to look at a faulty graph and kind of look through it and try to identify a universal structure. So this is cool. I've got some results here just quickly to show you what this might look like with larger graphs and different probability of success rates of the qubit forming in the first place. So the P on the right here, remember this probability is the success rate of a qubit appearing. So kind of the error rate would be 1 minus that. So in the first case, that would be an error rate of 5%. And then at the bottom, we'd have an error rate of 30%. And we can see that in all of these cases, although this is the finite setting, and get unlucky technically, but in all these cases, it appears that as we scale the graph up, it eventually can find some structure that is hexagonal within this lattice. And so, yeah, and so in fact, we can make the argument that we'll get into in a second, that the classical percolation thresholds, sorry to run all the way back, but the classical percolation thresholds that we looked at here actually define the phase transition at which it is no longer possible to find a universal structure within. So I just want to talk a bit about what the work of Dan Brown and others looked at, and they were trying to quantify the computational power of these newly found resources in a certain way. And one of them is using entanglement monotones. And this is sort of a way, well, it is a way of trying to quantify the amount of entanglement in a multipartite system. And this is very ill-defined. It's not clear exactly what is the correct way of doing this. But there is one way, there's a kind of a list of rules that they must obey and kind of to preserve quantum properties. One of the entanglement monotones that they suggest is understanding the computational power of this resource that we've identified, the hexagonal one within, is using something called the entanglement width. And this is because it's based, actually, the original development of this, I believe, was rooted in graph theory anyway. And it lends itself to this nice property, which I've written above, which is basically that the entanglement width of a product state is just equal to the entanglement width of the product state that gives the most amount of entanglement width, ignoring all the others. So essentially, if we have a cluster state, we just care about the entanglement width of the largest component in that cluster state. And that will define an upper bound to the amount of entanglement, loosely defined, available to this system. And so what's really cool here is because we're dealing with
Joe,
sort of, yeah.
sorry,
Hello?
just to cut in. The audio on your side is still cutting out sometimes. Would you mind turning off your video so that
Oh,
hopefully
I'm so
more
sorry. Of
bandwidth is
course.
sent to your... Yeah, thank you.
Of course. I hope, was everything, I can go back on anything if
No,
that
I
was...
think Zoom was sort of catching up, but like it created these like stutters. Yeah.
Okay, I'm sorry about that. I hope it's better from now.
Yeah.
So are we all good with okay, so I'll start from the entanglement width argument. Just real quickly again, we're basically looking at saying that the entanglement width of our system is just upper bounded by the largest connected component. And the reason we make this argument is because we're dealing with a cluster state. And so the cluster state is just sort of like, it is literally treated as a graph. So all of the components of this cluster state are essentially the same thing. They're just plus states connected with a CZ gate. And so our entanglement width are the available computational power, essentially, or the available entanglement to our system is just upper bounded by the largest connected component. And if we remember, the largest connected component is exactly what percolation theory looks to understand. And so there's a really nice thing here, which is that you can essentially make the argument that, and just to be clear, this is a reiteration of what Dan Brown and others have done. You can make the argument that the amount of entanglement, if you want to understand that as some kind of computational efficiency or resource available, is kind of just defined in terms of this load, like the upper bound is defined in terms of this largest connected component. And so if we plot these in terms of the probability values, you can sort of see what these might look like. So I've done these for the three universal structures we were considering: hexagonal, triangular, and square grid lattices. On the left, we're doing site percolation, so that's you remove a qubit. And on the right, we're doing bond percolation, so that's we're removing a CZ gate. We're counting for that being the error. And so one interesting thing you can observe here is that, first of all, there is a phase transition, which is slightly shifted depending on the structure we're looking at. And when we're in the supercritical regime, that's when we're guaranteed to have a infinite spanning cluster in the thermodynamic limit. And so essentially, we are almost surely kind of confident that if we are in the supercritical regime, our largest connected component will span the whole graph, and that will upper bound the entanglement available. And so in the site percolation setting, once we're above the supercritical regime, which is when it jumps up, this will scale linearly. And in the bond percolation setting, we essentially retrieve all of the available entanglement width to the system, because this is sort of upper bounding it. But you might be a bit confused here, because this is, it's providing us a loose sense of the amount of entanglement available to the lattice. But it's not necessarily dealing with the actual hexagonal structure that we've identified. And it's also not necessarily telling us whether, even if we had a structure that has a large entanglement width, so the largest connected component, even if it does exist, who's to say that that component itself obeys a universal structure? There's lots of, I believe there are some complete graphs even, which have a very large entanglement width, and they themselves are not universal. So there's no way of sort of guaranteeing this. And tree-like graphs can have a large entanglement width, and they themselves are not universal. So just because you have a large component and it's got a large entanglement width, it doesn't really tell us anything about sort of whether this thing is universal, how much of this universal resource we can use. So before diving into what we might do with this, we're going to consider the following argument, which is essentially looking at crossing probabilities. And crossing probabilities are just, if we consider a lattice, as the chance of finding a shortest path between both edges of the lattice. So if we look at any of these grids, it would be, what is the chance of having a path going from the bottom that can find its way all the way to the top, and the chance of finding a path that goes from the left all the way to the right. And an interesting thing about looking at these crossing probabilities is they're directly related to the largest connected component argument, which is that in the thermodynamic limit, we are dealing with an infinite spanning largest connecting component. And by definition, within that connected component, you can walk anywhere. So if it's spanning the infinite lattice, you make the argument that as n goes to infinity, n being the size of this lattice, we will always have a crossing guaranteed between both edges of this lattice. And we can do some numerical simulations to kind of see what we mean here. So in the top, we're looking at the simultaneous crossing probability. So there's a probability that I have a path occurring both from top to bottom and left to right in my graph. And again, we observe that this probability goes from 0 consistently in the subcritical regime, and then it jumps to being at least possible in the supercritical regime. And essentially what this means is that even if we get unlucky and we don't have these crossings appearing, if we had a large enough graph, we technically can guarantee that this probability will tend to 1. With a large enough graph, we can encourage the amount of crossing probabilities to appear. And so if we look at not just the probabilities, but now use the graph to count how many of these crossings appear, we get the results on the bottom left. These are exactly the same results that they find in the original paper, but we're just using our algorithm because it's simpler to explain. And so you can see again that sort of the number of crossings we get across our lattice go from 0 consistently to becoming possible again. Here in the SHP crossings count diagram, I'm normalizing it by the maximum number of crossings available, non-intersecting shortest paths available to the graph, which is why it's going from 0 to 1. And so the argument goes as follows. If we're guaranteed crossings above the supercritical regime, and we know that in a planar graph, crossings are guaranteed to intersect if they come from both sides. This is just a fact of planar graphs. We can look at how these crossings could intersect. So on the bottom right here, I have a thing saying at least degree 3 and at most degree 4. And basically, these are the only two ways that crossings coming from left to right and top to bottom can intersect. And so we, at least when they intersect, have a degree 3 intersection. And a degree 3 intersection is exactly what is required to form the hexagonal lattice. And so technically speaking, in the thermodynamic limit, as long as you're in the supercritical regime, you will always be allowed to find some hexagonal structure based on this argument. Because again, these arguments hold in the thermodynamic limit. So if you had a very large graph and you're very close to the critical value, it's probably very unlikely that this will actually happen. But theoretically, if you were to just keep blowing up this graph, it is still possible. So this is a question of possibility versus impossibility. And so in the thermodynamic limit, the supercritical regime is in fact sufficient for universality because you can always identify this hexagonal structure within. And so this is kind of nice theoretical arguments to look at this, can we find a universal structure? And the answer is yes, if we're in the supercritical regime. But now in a practical setting, we're dealing here with very kind of extremist results. And we're basically saying, if I have kind of like a lot of errors, my system might break down and, oh no, I won't have a universal structure. But we're more interested in what might we do to compensate? Because in the realistic setting, we might have qubits missing, and we might have CZ gates missing, but the errors are a lot weaker. They're not as strong. So what we can look at is the notion of developing an overhead. And in here, we're going to kind of promote quite a trivial notion for an overhead, but it's just to kind of picture what we might do to better quantify the notion of available computational power, because the entanglement didn't guarantee the sort of universal structure. So instead, what we're going to look at we're going to find something that we know is universal, and see how that compares in the faulty versus unfaulted regime. And so what we're doing here is we can count the number of bricks. So if we go back to the brickwork lattice, we would essentially look at the number of bricks that our algorithm can find in the unfaulted lattice and compare this to the number of bricks that the algorithm can find in the faulted case, and just take the ratio of those two. And then we define our overhead to just be the inverse quantity of this. And if we can show some results for this, and essentially what we have here is there's a few more translations, but we can plot the overhead in terms of the probability of success of the qubits appearing. So this would be 1 minus the error. And what it shows us here is, again, we have the manifestation of the phase transition occurring from percolation theory, but we get some odd scaling with the quantity of the overhead. And just to kind of loosely give some insight into what this means, is these graphs are basically telling us, the y-axis, the logarithmic y-axis, is basically giving us a number of how much we must rescale the lattice to return it to the available amount of computational power as if it was unfaulted. Now, we're quantifying this in terms of bricks, which is sort of a loose term for like computational power. There's definitely more sophisticated ways of doing this, but it's just a nice way to compute and get some idea of how these things might scale. And so we have in the black lines here, the reason these kind of things are stagnant and they're finite is because bricks are obviously a finite quantity. And so you can you have to scale it big enough to be able to account for another brick being able to be found in that lattice, which is why they jump. But we also do the results without flooring the calculation here, which is essentially equivalent to if we did this with like a larger lattice. So the black lines are computed, the actual like finite computation, and then we kind of do something with what would be equivalent to a bigger graph. And what's interesting here is that the amount by which we must rescale the graph, so the overhead, to compensate for this error, it does appear to scale pretty poorly, but it's technically polynomial when you're far away from the critical threshold, so towards the far right, between 1 and 0.9, even to 0.8. It was actually shown in the original paper that the scaling is finite, polynomial rather. But polynomial in a practical setting, which is, people love in the computer science community, it's obviously great to talk about polynomial scaling. And we're not necessarily talking about computational complexity here, but polynomial having to scale, say, the size of our graph by 4 times or 5 times to allow for it to have the same computational efficiency as if it was unfaulted is obviously quite a big deal. You can't just grab a cluster state and be like, oh, there's like a 5% error rate. We have to scale it 2 times. So, it's still quite expensive, the amount you have to rescale it. But fortunately, the errors we're dealing with here are not are sort of nowhere near the critical threshold here. They're a lot further. So this is some kind of illustration of how we might calculate an overhead for our problem. Now, the thing we've looked at here is 2-dimensional lattices. But in the practical setting, we also need fault-tolerant quantum computing. And in the measurement-based quantum computing setting, this usually requires implementing a 3rd dimension so that you can perform parity checks on your qubits, etc. And so an immediate way to extend what we've been doing would be to say, okay, well, let's just look at sort of percolation theory on a 3D lattice. So here we have a sort of simultaneous percolation theory where we're doing both bond and site percolation. And we're looking at what this would look like on a cubic lattice, because we're kind of arguing here. We're saying, oh, well, we just need a 3D lattice for it to be fault tolerant. So let's just look at the cubic lattice as an example. But the thing is, this isn't actually how errors occur when you're doing fault tolerant quantum computing, at least in some paradigms. Constructing these 3D cluster states is not as obvious as just building a 3D cubic lattice and hoping you can do it. There's sort of a sub-process that takes place. So we're going to look at a proposal that was made in 2021 by PsiQuantum. And they propose this sort of approach to constructing these 3D cluster states. And essentially what you do is you build qubits which have redundant legs, so other redundant qubits, and you attempt to make a CZ, you attempt to apply a CZ gate between any of the 2 qubits on there, which is in the top left, where we have these star figures, and we're attempting to apply a CZ gate. But these CZ gate implementations in the photonic case are non-deterministic. So they actually occur with 50% probability. And so there's a thing called repeat until success approach, which essentially just adds more legs. And it says, okay, well, if it fails, then my leg has been removed in the ZX sense, and I'll just reattempt it. And so by adding these more redundant legs, you can just repeat this process on these little microclusters until you succeed. And this increases the chances of your CZ gate actually working between these two qubits to around, I think with 7 legs, you get it to 99.22%. So you can blow it up much quicker to sort of a trustworthy rate of CZ gate application. And then all the redundant legs you're left with, you can just measure those out again. Right, so this is for constructing 2 qubits which are connected with a CZ gate, which is what I have in the top right here. But then it's a lot more difficult to try and repeat this process to build a cubic lattice. And so what we do instead is we introduce the notion of a type 2 fusion measurement, which is basically a form of Bell measurement, and we'll build lots of little lots of microclusters. So we perform the first process a couple of times to build little 6 rings. And then we take these rings that have been constructed and using the first process and perform type 2 fusion measurements to bridge those rings together. And then we can see how this brings us to the original form that we displayed here afterwards by combining these rings. Now, the type 2 fusion measurements that occur in the second process, they have around a 75% success rate with additional auxiliary qubits. So you can increase their rate to 75%. And so we're not just dealing with a 3D cluster state where the qubits can go missing and the edges can go missing. We're sort of dealing with a more complicated process where edges within the microclusters can fail, which is the first setting. You know, if we get unlucky and we perform it 7 times and it still doesn't work, we've kind of messed up the ring cluster. And we also have the fusion measurements that can be error. So it's sort of like a double form of edge percolation with different flavored edges. And to make things even more annoying, is by the time you've performed these type 2 fusion measurements, there's a chance that you suffer photonic loss, where the qubits in the microclusters themselves can go missing. So we're dealing with this incredibly confusing structure where we're performing little microclusters which can suffer both site and bond percolation. And then once we're bridging these microclusters together, those bridges themselves can suffer bond percolation. So how do we handle this? Well, we can just treat it in the framework of what is called graph renormalization, where you basically model the microclusters as a single node in a bigger graph, and then treat whatever it is of interest to our property as a single node site percolation. And so for simplicity here, we're going to be dealing with the case where either the CZ gate fails on the level of the microcluster, or bond percolation fails, site percolation fails on the level of the microcluster, which is when the qubit goes missing. And then on the bigger graph, we're just dealing with type 2 fusion measurements. So those are just sort of on the right graph, that would just be the black lines connecting the bigger nodes. And so for an example, what this does is we can define a property at which we remove the nodes on the coarse-grained graph. So in this case, we have a ring cluster. So if one of the nodes or one of the edges go missing, essentially the whole ring is unusable. But in a general case, you might be dealing with a larger microcluster where it can still be useful even if it suffers a few errors. And so to look at an idea of how we might treat this, we're going to say that we run these little simulations where we say we're dealing with a cubic level lattice at the global scale. So the cubic lattice, the edges between this cubic lattice are what are the type 2 fusion measurements. And then at each of these sites, they're actually representing microclusters. And on the left, those microclusters are suffering site percolation, so qubits are going missing. And on the right, those microclusters are suffering bond percolation, so the edges are going missing. And what we're quantifying on the level of the larger graph is we say, well, from the perspective of the larger graph, if that microcluster itself, which we're treating here just as, I think, 2-dimensional grid graphs, for example, the moment that graph, it can suffer errors, but the moment that graph itself is no longer universal, and we use the SHP algorithm to find out whether this is the case, whether it can find the hexagonal structures within it. The moment those microclusters are no longer universal, then on the larger scale, we treat them as though the site percolation has occurred on the larger graph. I kind of wish I had like a whiteboard here to better illustrate what I'm talking about. But I hope this kind of idea comes across. But we're sort of reframing this combined two-flavored edge percolation and possible bond percolation just as a different type of site percolation on a bigger graph. And so the results we get illustrated here, again, we're dealing with toy models. But the point is this is completely different than the kind of effects we would expect if we just treated them with classical combined bond and site percolation. The effects are higher order. And so by doing this renormalization, you account for them and can compute it nicely. And so again, we'll get these kind of phase transition periods because we're looking at, this is sort of, so the y-axis here, to be clear, is type 2 fusion measurement probability of success. And then at the bottom here, it's sort of the equivalent site percolation that occurs on that graph given the microcluster state. Right, so I hope that wasn't too much of a mouthful. Just to finish off everything I'm talking about is how this can naturally extend to the notion of hypergraph states. Now, hypergraph states, I don't know how recent this proposal has been, but from some readings, I think this is used in continuous variables, so CV quantum computing, and they've been proposed as a resource for these cases. And obviously, eponymously, they lend themselves to hypergraph states because they're applying multi-controlled Z gates, which are entirely equivalent to just sort of a hyper Hadamard edge, if you want, because any bipartite graph is equivalent to a hypergraph. And so I've kind of drawn that at the bottom here, excuse the gross sort of redrawing ZX hyper edge, but this is essentially what building a hypergraph state is. And the cool thing about this is that there's been lots of research, I think more recently, about percolation on hypergraphs. And so the motivation would be that, okay, if we have these kind of methodologies where we try and combine, first of all, sort of the nice symbiosis of ZX describing the physical structure of the graphs we're looking at, we've got all these percolation methods. Well, if we want to deal with hypergraph states and look at the robustness of those, there are results in hypergraph percolation theory that are already available to us, and we can just draw parallels with the methodology we've done before. And lots of these suggest that hypergraphs are in fact more robust to percolation. So their critical values, these percolation thresholds, are, I believe, higher. So they're more robust against errors. And it can help us motivate why it would be interesting to develop cases of using these hypergraph states. And so that's everything I'd like to talk about. Many thanks to Professor Renaud Lambiot, who is at the Mathematical Institute at Oxford, who helped me he helped me. This is my thesis underneath Renaud Lambiot, and he helped me a lot with sort of developing my ideas around this. And many, many thanks to Maddie Hoban, who helped me tremendously with sort of discussing these ideas. I met up with him a lot during this thesis. So thank you all for listening, and I'd be happy to answer questions.
All right. Thank you very much, Joe, for the nice talk. Do we have any questions in the audience? Yeah, KH.
I might go to the chat so I can see.
Hi. Hello. Hi.
Hello.
Do you really renormalize the lattice in practice? Because in my mind, if you do have any faults that are heralded, you just form these super checks and you move on from there.
Yeah.
Is that so in practice, like when you do run a practical quantum computer, do you really renormalize the lattice in some ways? Or is this more like a theoretical endeavor to see if you can get these universal structures back? Thank you.
Yeah, thank you. No, thank you for the question. I think a lot of the work we're looking at, and this is what sort of with the pre-processing algorithm, I think there's definitely like a theoretical endeavor. Like there's no notion of renormalizing the actual cluster state. This would be for pre-processing like theoretical development where you're trying to understand, say, like the phase, the percolation thresholds. So we're using this just sort of to simplify the methodology of understanding how these errors would affect the lattice. And sort of by doing this, hopefully you could use some analogy to calculating an overhead and help you, I don't know, develop more robust states in the future. There's no notion of renormalization on the like actual in the quantum computing sense. You're not doing anything to your system. All of this study is like high level, just looking at it from the theoretical perspective, trying to understand what it would look like. So renormalization is just, it's just terminology for basically accounting for the little microclusters as a single node. And this is just purely from a theoretical perspective to make it easier to perform calculations. I hope that kind of answers what you were asking.
Thank you.
Okay. Do we have any other questions in the audience? So I was wondering, because this implementation of this algorithm finding, that was implemented by yourself, if I understand.
Yeah, so
correctly?
the algorithm that we're looking at, this is my
Yeah.
version of the algorithm. So they do one just, this stuff, the approach, the idea to do this is what they do in the original paper, and they use they use like a right-handed walking algorithm where you just climb through the lattice. Now, this is more efficient, so they basically just start at some point and they try and climb through to draw these like little lines that we're dealing with.
Mhm.
Now, the reason I use the shortest path algorithm is, first of all, I think it's just like kind of simpler to explain just quickly when we're doing this. And also it helps, I think, bridge nicely with this notion of largest connected component. I think it's a lot nicer because defining shortest paths on a largest connected component when you're dealing with the infinite case is like a guaranteed thing. You will have some path between them. Whereas if you're talking from the random walk perspective, it's kind of less obvious to claim that you can like walk through a connected component. It's more like it helps with, I think, building on the argument of the largest connected component. No, but these algorithms, they're just implemented in Python. So yeah, you just climb through them. In the original thesis, there's the code to do these. They're kind of fun to run.
Yeah, I was just wondering on like the runtime for this kind of thing, like how
great
quickly
question.
does it?
Yeah, so I think the shortest, so calculating the shortest path would sort of a more complicated thing than doing the walking through. I'm not sure the exact computational complexity of that. Wait, maybe I'll turn off the video because I think my audio is chopping off. But the original algorithm, which is sort of entirely equivalent to in terms of the results we find, is polynomial in, I think I had the results here. So basically the original algorithm, I'm not sure the running time, to be honest, but in terms of performance, it's guaranteed to find around P crossings when you're away from the percolation threshold. Or maybe I think that's meant to be OL actually. I'm not sure. I think that makes sense. Yeah, OL crossings.
Yeah. I was just wondering, like in terms of like practical performance, like is it seconds, is it minutes, is it milliseconds? Like how long do
So when I was running it, I think like this kind of thing, just finding like doing all of these manipulations. Once you scale it up, I think it'd be like, yeah, it's like a couple of seconds. It's like 3 seconds memory. I cannot remember the exact implementation, I'm afraid. But it would definitely be, I think if you want to look into this from the perspective of the algorithm itself, it's much better to look at the original paper, because that's sort of the focus of that paper is very much the algorithm implementation and like the runtime. The reason I kind of developed this different method is, first of all, just to illustrate it quicker and just to develop on the ideas of universality and kind of help with the arguments made for the later sections. But if you are interested, I definitely recommend reading that original paper. There's some good arguments in there.
And your thesis title, like it starts with categorical quantum theory. Like I was wondering, is that just because you're doing ZX stuff, or is there like a more deep connection here between category theory and percolation?
So because I was on the MTP course and my supervisor, he's from the background of like percolation theory, network theory. I just thought of giving it the title categorical quantum theory because there in the original thesis there was a section of just talking about how ZX calculus emerges as string diagrams from category theory. It's nothing more than that. I was just trying to give it that title to make it sort of more accessible than calling it ZX calculus for someone who may not be familiar with ZX calculus.
Yeah.
That's all there is to that.
Nice. Okay. Do we? Oh, I see there's a question in the chat. I'll just repeat it for the benefit of the video.
Yeah.
Is there much opportunity for speed up if you were to know what circuit were to be etched? Like how much do we lose by converting to a specific non-faulty lattice instead of etching the circuit into a faulty lattice? Yeah.
Mm. Yeah, that's really
So,
interesting. So, let me just read that, make sure I understand exactly what you're asking here. How much we lose by converting to a specific non-faulty lattice instead of etching the circuit?
Does it make sense?
So I guess the question would be like you're going to a triangular or hexagonal lattice, but to do a computation on those, you would also like cut away a lot of the graph, so you end up with like a very small thing. Because it's
Yeah.
universal, but it might not be universal in the most efficient way. And if you know the
Completely.
computation you're going to do, like if you have a specific ZX diagram with a specific graph, like you could percolate towards that thing directly instead of going through the triangular lattice first.
Absolutely. I think that's really interesting. Sorry?
No, exactly. That's what I mean. Yeah.
Okay, great. Yeah, no, I think that's a great question. So the reason we're looking at hexagonal lattices is because just from the computational perspective, a hexagonal lattice, as we made in the argument here, is sort of the one where you can guarantee, like in these thermodynamic limit arguments, you can guarantee a degree of at least 3, and hexagonal lattice is the universal structure we know with degree 3. So it'll be the one that we're most likely to find. But indeed, if we like had a specific computation that we wanted to perform, doing this hexagonal finding is obviously not very efficient. Like there's clearly a lot more resource capacity available. And I guess in that case, it would be interesting to try and develop better algorithms to look at this. The reason we're doing the hexagonal stuff, although it's computation inefficient, is it's just to make it hold up for these sort of scaling arguments when you blow it up infinitely. But indeed, yeah, I'm sure it'd be super interesting to look at, if I have a desired, circuit to implement, maybe there's some way of like looking through the graph and trying to see where I can put this algorithm instead of just being like, oh, well, let's throw a hexagonal lattice. But I can't give you any numbers with regards to what that,
Nice.
the efficiency we're losing. But I think it's really interesting as a proposition.
Yeah, nice question. Thank you.
To maybe give a reason why it shouldn't work, I think you will be solving the subgraph isomorphism problem if you're trying to do that. Like if I have like a big graph and I want to know, does this smaller graph fit in there somehow? That's the subgraph isomorphism problem, and that's a hard problem.
Yeah, it is a hard problem. That's true. So,
but then like for a specific subgraphs, it can be it's easy, right? So like if you know your specific circuit, like you can, or like for families of graphs, like it's easy to get them.
I guess like for example, if you wanted instead to look for like a square lattice within the original lattice instead of a hexagonal, the problem is it's a lot harder to make the argument that you're guaranteed to have degree 4, which is what is necessary for a square lattice. And so the moment you move to finding universal lattices with larger degree counts, so if we look here, well, the less likely you are under percolation to be able to find qubits with this amount of degree available to them. So I reckon, like depending on the universal structure, I'm sure there'd be a nice way to use percolation theory results to make an argument that sort of, hexagonal lattice you're likely to find. In fact, you can guarantee it. When you get to square lattices, it probably, again, the moment you span it infinitely, you can guarantee it. But on the finite setting, it's probably the probability of finding those square lattices is probably weaker than hexagonal. And then for triangular, it's going to be even weaker because they've got a higher degree count. They require more intersections.
Yeah. Cool. Thank you.
Okay. Do we have any other questions in the audience?
Can you expand a bit more about the hypergraphs? Sort of percolation threshold of hypergraphs.
Yeah, I mean, so this is okay. So like when you're dealing with hypergraph states, essentially, I'm to be completely honest, I'm not extremely read up about the physical implementations of these, so I don't want to give any equivalent to kind of static and dynamic preparation. But essentially, it would just be that if we treat similar to how we treated the graph state creation process and we subject it to errors, if we were to deal with kind of controlled Z-gate errors, they would sort of manifest in different ways, because if you lose an edge between here, it's not exactly that you've lost the full computational ability. You're still left with a standard CZ gate. And there's some ways where this can still be useful, I believe. Essentially, hypergraph percolation would be just the analogous study of percolation theory, but on hypergraphs. And because of this kind of more complicated system, they're shown to be more robust. And so that's essentially it. It's just an argument of saying that the tools percolation theory already exist, and they're good for studying erroneous graph states. If hypergraph states are subject to similar errors, there is methodology out there. There's literature that has studied this. I don't know what kind of details you would like about this. I'm not sure if I can be much of use to the full extent regarding this. Is there anything particularly you want to know?
No, that's great. Thank you. Thanks for the explanation.